Hello, and welcome to today's SEI webcast, Improving Analytics Using Enriched Network Flow Data. My name is Shane McGraw, Outreach Team Lead here at the Software Engineering Institute, and I'd like to thank you for attending today's event. We want to make today's webcast as interactive as possible, so we will address questions throughout today's talk, and again at the end of the presentation, and you can add those questions into the YouTube chat area at any time. We will get to as many as we can. Our featured speakers today are Dr. Tim Shimeall and Katherine Prevost. Tim is a senior member of the technical staff within our CERT Network Situational Awareness Group of the SEI, where he's responsible for overseeing and participating in the development of analysis methods in the area of network system security and survivability. Welcome, Tim. Looking forward to your talk today.
Thank you, Shane. Looking forward to
Joining Tim, we have Katherine Prevost, and Kat is a senior engineer with the CERT Risk and Resilience Directorate. She has nearly 30 years of development experience, including the last 18 within our CERT division. Katherine, thanks for joining us today. I know you're feeling a little bit under weather. We appreciate you being here.
Thanks. It's great to be here.
So now I'm going to turn it over to Dr. Tim Shimeall. Tim, all yours.
Thank you. And this is a topic that follows on from a presentation that Katherine and I made at FlowCon 2023. We'll probably mention a little bit more about FlowCon at the end of the talk, but it derives from a experience that the SEI has had looking at network flow data over the last 3 decades and across a variety of different networks, ranging from small home networks, exercise networks, up to city municipal networks and national and international network data. So a lot of the concern that we have is making sure that we can do analysis that looks at security issues and it helps inform security decisions, but do it in a way that will scale to very, very large networks and very interactive networks. And today we're basically going to have a conversation, and the conversation is going to work around a problem statement that we have in dealing with making sure we've got enough detail in the data that we're dealing with to be able to draw reasonable conclusions and to observe factors that are reasonable to us. We're going to talk about it in terms of packets and flow data. Then we'll talk about enriching flow data. Then we'll get into the mechanism we use to gather the fields for enriching the flow data, deep packet inspection, and we'll walk into an example using DNS abuse. There'll be a series of different solutions that we'll be talking about today, including YAF and Mothra, but a lot of these are derived from work that the SEI has done in this space. The basic problem we're dealing with is how do we more precisely identify aspects of network behavior without giving up the size and coverage benefits of network flow? And this is the big argument for network flow, is that I can summarize a lot of traffic in a very concise summary. I can take tens of gigabytes of traffic and reduce it down to something that is recorded in tens of bytes. And that's a huge advantage because it lets us deal with very large networks. It lets us retain data on behavior over an extended period of time so that the network defenders have an established baseline of activity that they can do to better understand what the traffic is. The drawback is if I'm taking tens of gigabytes of data and reducing it down to tens of bytes of data, I'm giving up a lot of detail. And in some cases, that detail, the loss of detail obscures the nature of the network traffic, and particularly may make it difficult for us to tell whether this is normal benign traffic or isolated malicious traffic. And being able to make that decision is a really key aspect of a lot of the analysis goals that we have in dealing with this data. So on the one hand, if we want full detail, well, about the fullest detail that we can grab at a network level is to grab every packet that goes by and all the contents of that packet. The header fields, which are essentially like the address on the envelope, talking about what kinds of ports and protocols and source and destination addresses are dealing with it. The packet content, any nesting of protocols within protocols, all that's visible within the packet, the full packet data. Everything's preserved. Everything that is observed is preserved. But as you might imagine, if I'm recording tens of gigabytes of data, I need tens of gigabytes of storage to do that. That loses the aspect of, if I've got that volume of storage, I probably can't afford to keep it around for very long, a matter of days. The problem is a lot of network attacks aren't known within that time frame. They aren't detected until weeks and potentially months later. And that makes things very difficult if all we have are the most recent days of network packet data. That historical record is going to be limited. Furthermore, backhauling all of this data to a central analysis point or scanning all of this data is very challenging. You're dealing with large files. You're dealing with complex situations. It could be a problem. But the big advantage is any traffic that comes across can be examined in really full detail. We've got high fidelity of what's going on when I'm talking about packet captures. On the other side of the spectrum are the classic flow records. Classic flow records are basically a call record across the network. It doesn't tell you all of what was said. What it said is this machine was talking to that machine, and they were talking using that protocol, and they exchanged this amount of data, and the conversation occurred at this time, and it involved and it ended in this manner. That kind of information is left on there. The details of, well, okay, what host names were being used, what applications were involved, where did that data come from, did that data have any proprietary nature to it, all of that kind of information just simply is not available in the classic flow records. But the big advantage is it's small, which simplifies gathering the data, it simplifies transporting the data, it simplifies the processing needed to actually store the data, and really reduces the cost of retaining the data for very long periods of time. But at the problem is we've got this limited detail. It means we really need to put a lot more work into understanding patterns of behavior to infer intent, rather than being able to directly observe intent. One approach, there are several different approaches for dealing with this. There are other solutions which are out there. For example, network packet traces are done to just isolate out the header fields, this address information, but they do it on a packet by packet basis rather than a conversation by conversation basis. And that gives us more detail as to how much was exchanged where, without the full size and complexity of it. But the problem is it tends to focus the detail on what's going on in each packet rather than what's going on across a communication. So what we'd like to do is get the advantages of flow records, but do it in a way that increases the amount of detail available to the analyst to try and understand what's going on our networks. And this brings us into a solution referred to as enriching flow data. And we can enrich flow data by looking at a statistical level. We can say, okay, as we're assembling flow records, can we add in more information about the summary that's there? Add more fields to the summary that gives you an idea of, okay, is this, when I say the total information that flowed across the network, is that flowing all in one big lump? Is it flowing in roughly equal sized chunks? What's the spacing between the flowing and things like that? Those are things that we could capture and augment to it. That's additional enhancing flow statistics. You can take a look at the entropy measures and say, what is the degree to which the information is consistent versus what's the degree to which it bounces around. That's there. We can do application labeling. Application labeling basically says, okay, in addition to the port and protocol information, can we actually look at the traffic and see whether or not that's actually the protocol that's in use, or there is an application like web traffic or email or file transfer going on that we can label and know that that's actually going on by recognizing the setup information from as packets are exchanged. We could do partial payload, and there are solutions such as Argus that do that, and capture what is the traffic at the initial end of the communication so that you can see the setup information. And often that setup information in and of itself gives you a good idea as to whether this is a normal communication or there's something odd about it. We can also have expected behavior of the behavior of the traffic. So I would normally expect, for example, a web page to be one transfer kicking off a whole series of smaller transfers as the various fields and content of the web page populate. Is that the model that's being shown? Does it look like a page load? Does it look like a webinar where there's a stream going on and an ongoing higher volume on a continuing basis? This webinar, for example, will go on for about an hour, and the traffic bandwidth will be fairly high across that. There's not one initial big kickoff followed by a bunch of subsidiary transfers. By being able to have rules which can recognize things like that, we can better characterize what's going on on the network traffic and whether or not that matches our expectations or our security concerns associated with it. Finally, we can do deep packet inspection. Deep packet inspection is where you take a look at the various types of traffic that are going on. So do we have a Internet Protocol data transfer that implements the Transmission Control Protocol, TCP, that supports web traffic, that holds an embedded conversation that is actually implementing a DNS lookup? So you got a 5-layer cake of traffic going on. And at what we'd like to do is be able to capture activity occurring at the relevant layers of this cake and be able to pull them out and make them visible to the analysts so they can understand, okay, it's not just a web session, this is actually a DNS lookup, and be able to treat it like a DNS lookup and incorporate it within the information gathering that would occur. And this is really kind of the direction we're talking about today. We're looking at some of the tooling and some of the capabilities involved in extracting out the salient details and incorporating them within an analytical solution. All right, having reached this point, this is kind of setting the scene of what we're going to talk about. Shane, have we gotten any questions so far?
No audience questions, Tim, but I did have one myself, and maybe you're going to get into this. The question being, just how long has the SEI been active in analyzing network traffic? Is this something you guys have done for a while?
Indeed, we have. And we've been fortunate to have some evolution of this behavior. We actually got into this space in late 1999, just as a result of some technical developments occurring at that time and a need on some of our sponsors to be able to better track what traffic was flowing across their network. That tracking involved being concerned about network threats. It also involved just simply understanding, are we supporting the protocols we should support? Are we reaching the audiences we should reach? All of that kind of information flow becomes part of the network situation, and hence network situation awareness. Our initial solution was a flow collection and analysis solution known as SILK, the System for Internet Level Knowledge. And SILK processes classic flow records with very limited enhancements. It does actually have application labeling via a traffic collection system known as YAF, or yet another flow meter. And YAF and SILK are still in wide use today across some very, very large networks. But over time, we've become more and more aware of their limitations and pressing of it. And we have some newer solutions that we have developed that's in place. So SILK's still being distributed. It's not obsolete. As a matter of fact, there's another release coming forth in the next few weeks. But there is, we do have other solutions which have started to apply. Solutions which give you access to data on a more timely basis, and solutions which give access to data using a more full semantic of the communication that's going on. And we'll touch on that latter, Mothra, a little later in this talk.
Great, thank you for that, Tim.
All right, so what's deep packet inspection? Well, classically, flow includes information from a couple of different network layers. Most of the information comes from either layer 3, which is the Internet Protocol layer, or layer 4, which is the transmission protocol layer. The Internet Protocol layer gives us the number of bytes in the communication, the number of packets in the communication, what's the source and destination addresses, what's the IP version number, is this an IP version 4 or version 6 communication. That information basically comes from layer 3. From layer 4, you get source and destination ports, you get flagging information. If it's ICMP information, you get ICMP types and codes. If it's not TCP, UDP, or ICMP, well, what is it? Is it ESP, which was used in some VPN solutions? Is it unknown or undefined transport protocol, which may indicate proprietary traffic, or it could indicate malicious traffic? As we're collecting that data, we can, that data essentially, like I said, is the envelope information. As we're gathering off that, we can also peek inside the envelope and say, okay, what's actually being carried? What is the semantic of what's going on? If this is a DNS request or response, can we capture what domain is being looked for, where the responses came from, all of that kind of traffic that we normally, is this an authoritative response or a non-authoritative response? Pardon me. All of that kind of information we can capture and incorporate by defining additional fields for the flow records. Historically, this has been hard because the flow record format has been hard-coded into the collection and analysis tools. In recent years, as we've seen the development of more standard data formats and extensible standard data formats, this has become much easier. And in one particular extensible format is referred to as IPFIX. So IP Protocol Flow Information Exchange Protocol. And that defines a much more flexible record structure that allows you to add in additional details depending upon your needs. Also useful is some authoritative information about if there is encryption going on, what kind of encryption is it, what keys were involved in doing it, if there was authentication in place, what authentication keys were present, at least by key ID, those kinds of things. But recognize how much information is included and which information is included is a fairly complex matter. As you're doing deep packet inspection, you tend to run up against privacy concerns. So if I'm collecting emails, do I want to collect the subject header of the email? Well, the subject header in and of itself might reveal proprietary information and might be of concern to a lot of organizations. So, that's something that's in place. If I'm going to store host names, is that host name information authorized to collect within the country that's in place? In the European Union, IP addresses are considered proprietary or protected information, host names more so. And in that case, you really want to be able to conform to your local legal structure, your local privacy laws. So there's a lot of choices that are involved here as to what data you want to collect, which fields you're authorized to do so by policy or by law, and how long you want to retain and how you deal with destroying some of those. But once we have the DPI information, we need to recognize there are some things that are in place. Deep packet information doesn't always line up directly with flows. So for example, if I have multiple email messages, the multiple email messages may share some common features, source and destination, things like that. They may be transferred in one long transfer, but the messages will be separate. They'll have separate date time information. They may have separate date time information because of closely associated messages may all be transferred in one SMTP transfer. You may see responses coming back that you'd want to associate with them. The response would appear as a second flow that's in place. So being able to collect and to align DPI information presents some technical challenges. For DNS, DNS is a protocol where a host wants to identify a foreign host. So my computer sends out a message saying, hey, who owns IP address 10.0.0.6? And it gets back not one response, but a whole collection of responses that may say, okay, Shane's computer is 10.0.0.6, or Katherine's computer is 10.0.0.6. And those variety of responses we would like to be able to associate together and flag the whole thing as one communication, because fundamentally it is. I'm sending out a request, I'm getting a bunch of responses back. But the separation, the bunch of responses makes it difficult to say this is all one flow in the classic sense of a flow. So we need to be able to align things properly as we're dealing with it. It is also a case that the more data you have, the more questions you can ask. And the more questions we can ask, the more we can discover. But there are also more ways to ask the question wrongly. So I may say, I want to see all big DNS records. Okay. DNS records that are larger than the average. Because the argument is, if there's data transfer, it might be being done through big records going on. Well, it turns out there's a lot of other things that make DNS records big. It could be a complex query in which it needs extra fields. It could be a query that results in a series of responses that give us slightly different answers to the question. Canonical names versus normal names, network level information versus host level information. All that can be mixed into a single DNS response. And so that tends to make a big record that would be normal and expected, not suspicious or malignant. So you have to be careful about how you phrase the query. And we also have to have ways to very carefully phrase our question, or very powerfully phrase our question, so we can isolate down to the traffic that is just relevant to the problem that we've got. And that means we need to go beyond just simply having a tool we can use command line parameters to, and into saying, I need to express this in terms of a language, and be able to say, this is a long record that doesn't contain a lot of separate responses, but instead is just a few responses, and those few responses each have these characteristics. And that's a complex query where I'm staging all those things together. And doing it in a simple command line tool is very difficult. Doing it in a powerful language makes it much more simple. Now, which powerful language? That's a different story. There are several different scripting languages that are popularly expressed. Python, SQL, things like that. We're looking predominantly at using Spark with the Scala language, Spark solutions with Scala language, largely because we want to key into some of the big data solutions that are out there and be able to meld together data that is fairly rich, and also have the power to doing it. We could have designed our own language. We chose not to, largely because you define your own language, you're the only one that has to teach it. You have to support it, and that leads to confusion. Being able to use an existing language that people are already trained in makes things much more efficient. Shane, any questions at this point?
No, I just had another one, Tim, of asking, talking about past efforts again. What has the SEI's past efforts been in adding deep packet fields into network flow data? Can you give us a little history there?
It started by looking at saying, well, we want to go further than just the transport. We want to look at see what the applications that are going on. And that's what led to application labeling. We've done application labeling for expected applications like SSH, email, web traffic, SSL traffic, work like that. We've also looked at specific sorts of malware, the classic poison ivy, certain remote access Trojans, things like that. We look at and can identify within the network traffic automatically. But even as we did that, we recognized that was sort of approximate solution. What we really want is a more full data capture. And that's what motivated this particular work.
Great. Thank you for that, Tim.
And certainly if people have questions, I would encourage them to ask. The situation works out much better if the conversation expands. So as we started to get it to have this desire to look deeper into the data and pull out deep packet inspection, well, that's when we got into looking at how do we enhance our flow collection. And the flow collection tool, the flow generation tool, is YAF. YAF aggregates packet data, particularly packet header data and also selected packet content data, and populates records in the IPFIX binary protocol standard. Binary records are used rather than text-based formats for space efficiency, and also to preserve the semantics of the data effectively. Katherine, do you have any comment here about YAF and the design choices made there?
Something a little bit related to what you were just talking about with that last question actually is we're experimenting at the moment a bit with how to do some of these nested structures in IPFIX information, just in terms of you mentioned SMTP messages can have like multiple attachments, and of course multiple SMTP messages for a single connection. And that nested kind of structure, it's complicated to represent and it's complicated to query. So for example, we're trying this out and we're trying to see, is it possible to get some good use out of that versus some older models we did where it's basically just like, hey, let's just look for all of the subject lines and we won't worry about what message each one is connected to or what message each attachment is connected to. So you can't really line up this subject goes with this attachment. And with a nested structure, you can make that connection. You can say this subject goes with these attachments, this subject goes with these attachments. But it's harder to ask the questions. It's harder to pull the data out of that. So, it's a complicated space, and we've got a lot of choices, and we're trying things out and seeing what works well. I hope.
Now, in response to that one, there is a lot of choice for configuring the flow collection. And YAF does produce very large records containing structured deep packet inspection information within its binary format. But it's also capable of incorporating more complete packet snippets. We've seen it being used to do partial data capture or to map flow data onto packet data collections and vice versa. That can be very, very useful as an analyst if I do have some packet capture laying out and I'd like to preserve parts of it for later analytical use, or I'd like to match what I observe in flow data to the more full data available with full packet capture. But YAF's focus is simply on aggregating the packet data into flow records and building the flow records in the IPFIX format. It doesn't have query capabilities. Its job is simply to gather the data and store it efficiently, or as efficiently as possible, given the detail and structure of the data. We have a variety of tools which then process the IPFIX format records, including Mothra. Mothra is a library that augments Apache Spark to allow you to load, analyze, and process IPFIX format data in this binary structure. There are a lot of tools around that allow you to store and partition the flow data for later retrieval. There are also other tools which deal with close to real-time analysis of the data on a flow-by-flow basis. But we're really not dealing with that today. If you want more information about that one, take a look at the distribution site that we have, which is www.tools.netsa.cert.org. NetSA is NETSA. And that has full documentation of a lot of these tools. Mothra reads IPFIX records directly, including the structured DPI information, and then it makes the IPFIX fields available for Spark queries, and using the full power of the Apache Spark language, which allows you to build data frames and analyze things in terms of data frames as you move across and deal with things effectively. The data frame format is standard enough in the industry where there's a lot of people that know how to deal with it and move things forward in a fairly productive manner. We're going to take a look at an example case. The example data set that we're using, it was actually collected on for an experiment up in Canada. It's available publicly at this URL, and it's also described more carefully in the paper cited at the bottom of the slide. The authors kindly allow us to redistribute, republish, and mirror their data set in any form, but they do insist that any distribution include the citation as being the CIC Bell DNS EXF 2021 dataset, and refer to their publication of it at a conference in China. So the particular application we're looking at here, we have traffic. We suspect that there is actually data exfiltration occurring across DNS traffic within this data set. What we'd like to be able to do is differentiate the information of when it's typical data and when it's suspected exfiltration data, and be able to characterize those two sets in a way that's pretty detailed. If I go into and use a standard silk command, about as far as I can go is saying, okay, load a data set, lightbenign.rw, filter out DNS information by saying the port information or the transport data involves port 53, which is the DNS, and then feed it into another tool which can characterize the data. And the particular characterization is, okay, for each source, how many flows, how many bytes, how many packets, and restrict this to sources that process 10 packets or more, and 200 bytes or more within there, within all of the aggregated packets. And so using that, I run through this, and I discover this data set has traffic coming from two different IP addresses. One is 8.8.8.8, which is the canonically known Google Open DNS resolver. And the other is a private DNS resolver at 192.168.2038. And that private DNS resolver was actually stood up by the operators of this experiment. If I go into, that's about as far as standard flow data would give me. It's occurring using this volume information. The volumes are unsurprising. There's a lot of roughly equal amounts of flows, with more bytes going to the public resolver than to the private one. That's fairly expectable range. The number of packets is very similar. So it argues that packets coming back from or involving 8.8.8.8 tend to have more full information present than the ones coming from the 192.168 address. But I'd like to look further. So to look further, now I want to be able to dive deeper into the packet data and extract out more details. I'm going to use Mothra for that. Mothra is invoked by bringing up Smart Shell and loading the Mothra library into the Smart Shell, and then feeding it a series of commands. And the series of commands are a command script. I'm going to call it DNS ID benign.sc, and it produces a much more detailed summary. As you can see, it contains a much more full address. I'm looking at a domain address rather than just an IP address. So I see what DNS name is coming back. It's not none of these addresses are fully qualified domain names in the expected sense. Most of these appear to be reverse lookups and reverse responses. That's confirmed by looking at the DNSRR type. The DNSRR type of 12 indicates this is a reverse resolution that's in place. By breaking up by DNS name and RR type, I don't have just one big clump of records, 15,500 records. Instead, I can break it out case by case in a much more detailed fashion and see which addresses are really involved in the traffic. And I note the big one here is the 252.00224, which has about twice as much resolution as anything else, and about twice the byte volume, and about twice the packets. But that's all occurring between one source address and one destination address. So all of these are moving forward probably there. One of those addresses is probably the 8.8.8.8. address. This is what my script looks like. Admittedly, I had to break it into 2 columns to fit it on the slide, but it's still a relatively short script. It basically says, okay, I want to import the Mothra library. I want to import the fields, the IPFIX fields that are part of that Mothra library. I want to load the data from a known data directory. And the particular one I want to load, since this is the benign case, I want to load lightbenign.ipfix, which I generated by taking packet data and applying YAF to it. Okay. And if for the case that I'll be presenting in a second, where I have suspected exfil data, there's a DNS ID abuse case that basically differs from this script, only that I'm loading a different file. And that's what this commented structure basically means. Then I can bring in and say, okay, build a data frame. I want to build a data frame populated from a set of IPFIX fields. And it's a quick and easy thing. I want to bring in IPFIX fields. I want to bring in all the default ones. And I want to bring in the DPI fields for DNS. And I want to read them all in from an IPFIX data file. And that, in and of itself, gives me a data structure to load. Once I have that data structure, I can apply a lot of very conventional things. I can filter the structure. I can summarize the structure. I can group the structure, and I can reorder it to have a more visible thing, and then display the parts of it that I think are relevant. And that's basically what's going on for the rest of the script. I'm going to filter out traffic of interest, which is the port 53 traffic, identified by the application label, and those that have a DNS record list that's greater than 0, so it's not only DNS traffic, it contains DNS information. And then from that DNS information, I'm going to extract out, I'm going to focus on start time, IP address, source and destination IP address, how many packets, how many bytes are flowing across, what's the DNS record name, what's being queried for, what's the resource record resulting from it. That's a list of resource records. And then I'm going to group it by the resolution name and the resource records, and then start to aggregate the fields and say, okay, based on that, for each DNS name and record list, I want to know how many flows, I want to know how many source addresses, how many DNS destination addresses, I want to know how many bytes, and I want to know how many packets. And then I'm going to further filter and say, okay, I'm not interested in ones where there's less than 20 less than 20 or less packets. I'm not interested in ones where the byte per packet ratio is less than 70. I'm not interested in those where there's more than 3 names being queried for, because that in and of itself will expand the data. And then finally, order it by the number of bytes being communicated and show me the top 100. Katherine, you're the implementer. What did I bobble up in the description of the script?
That was all correct. One thing I would call out is when we talked earlier a little bit about how it's easy to ask the wrong questions at times. And here's a case where Tim and I had to talk a bit about this because where you get down to the some octet count and some packet count type stuff, it's important to remember that those are the aggregate sizes of all of the packets that involve this name, not just the name, the stuff related to the name itself. And that changes the context of this a little bit. Or we're ending up with the names for DNS responses that have a large byte to packet ratio for the whole packet, regardless of what other names are involved. So that's one of those kinds of subtleties that can come out when you have this nested structure and when you're combining a couple of different collections of things. In our case, we have things aggregated by flow, and then we have some other details that are coming on a very sort of packet by packet basis, and even finer detailed, and the statistics, yeah, it gets a little messy.
Well, this brings out a couple of points that should be made at this point. One, it's very productive to not be constructing an analysis in isolation. Having people with a mix of expertise is really important. I lean very heavily on Katherine's detailed knowledge of the language semantics when operating as a data analyst and saying, okay, how do I put this together? And if I put it together there, what actually am I asking? Secondly, you really have to know your data. So as you're going through this process, there's an exploratory phase where you're really looking and saying, okay, what data is within my data set, and what fields are available and what are not available. And being able to know that in depth builds your capability as an analyst to really refine and understand what's going on. So yeah, there's a lot of, this was the final script. This was definitely not the initial script. We went through a whole bunch of iterations on this as a dialogue between Katherine and I. So in looking at the abusive case, okay, here again, the top part is looking at the flow data, classic flow records. And again, what you see are how many flows, how many bytes, how many packets. Here's the case where when they were doing the data exfiltration, they transferred from using the Google resolver to a second local resolver, 20.72. And this second local resolver was the intended recipient of the data. Now, that change in behavior in and of itself could give you some insight and some desire to work further. But looking at it in much more depth, okay, you've got the case where you've got the 252.00224 data looking at the Mothra data now, and looking through that, the initial top entry is basically the same information has occurred in there, but I'm seeing some other data addresses pop up and some other data sizes pop up, and in particular this 2.20 address, which actually you should read in reverse for a reverse lookup. That actually was the recipient of the data exfiltration. And we can spot this by the fact that although there weren't that many flows, there were almost as many packets and very close to as many bytes being transferred. And that in and of itself was somewhat suspicious. So that let us isolate the fact that, oh, wait a second, there's something going on here that deserves deeper investigation. And at that point, you could look at who's communicating with this host and look at what's the status of that host and start to trigger into more data analysis to pull things forward at that point, and host analysis.
Tim, a quick question from Benjamin asking, is this based on sampled or unsampled flows?
These are unsampled flows, but it's pre-collected data. The experiment collected it as full packet capture, and then we just turned them into unsampled flows.
Thank you for that.
Okay. Any other questions that popped in?
That's the only one in the queue right now, Tim.
Okay, great. Well, we're a little bit before the end of time, so we've got some further time for questions. The point is, we know we want to look deeper into the semantics of the network communication. And the way to do this is to be looking at extracting not just transport information, but application information, and be able to analyze it in a common format. There's a variety of approaches for doing it. We've talked about one of them today, using a solution that supports IPFIX. Using the flow information with additional DPI fields allows the network operators to balance storage volume against precision. And storage volume often keys to data retention. and the scope of things that can be analyzed. This tends to, by adding further detail, that tends to improve the degree of actionability of the results. So we can say something's not just suspicious, but these are the specific characteristics that suggest that this is potentially malicious. This may also slow down the production of some results because you are increasing your data volume, you are increasing your data velocity, and that tends to add to the need for more processing and heftier processing. This DNS example is actually recently published in a CERT blog post. So if you want to see some more detail of how that solution walked through, take a look at the recent blog post that I authored, and it's out there. It is already on public on the web. So at this point, Shane, I'm going to turn it back to you for any further questions.
Sure. We had a follow-up from Benjamin asking, what are the resource requirements for YAF?
YAF itself is actually fairly lightweight. A lot depends upon the volume of the network you're dealing with. If you're talking a home solution, well, we've even had a case where a home solution was implemented on a Raspberry Pi with a fairly light structure. If you're talking a larger infrastructure, you want dedicated processing resources. But they're for a small to medium network, that's something that can be done with commodity hardware. Katherine, can you step in and with anything about larger or more complex environments?
Mostly, I would say that, like anything where you're doing network monitoring, the place you have to start to look is where you're getting into dedicated specialized hardware for collecting network taps and things like that. So once you start getting up into giggy and multiple giggy range, you gotta think about how you're going to do that, and it's possible to do it with YAF, but it's definitely a kind of thing where you have to think about how to architect things and how to get the data where it needs to go, and what equipment you're going to use to do it, because it's not as simple as just throw a network card on a box and have it go to promiscuous mode at that point. I can't really say much more than that without knowing a specific kind of network environment in mind, but I can say we've got sponsors using YAF on very large networks. So
one thing that is the case, YAF is designed to federate. So you can have multiple instances of YAF collecting data, and that data gets federated in a consistent format. So if you do have a complex network where you've got a lot of taps moving, or a lot of access points moving out of your network, you will probably want a monitor on each access point, and then treating and being able to trace what's occurring across access points or within one access point is supported by the information collected by YAF. There are other solutions out there which federation becomes much more difficult.
The next one I have, Tim, is I remember this might have been a little bit older, from a couple of years. You hear about DNS hijacking and it being a major problem. I don't hear about it as much anymore. Is it still a big problem, or organizations just better equipped to handle it?
Well, there is a lot of more effort on the part of organizations to authenticate their DNS communications, to have DNS gateways, to have DNS filtering going on, to try and deal with a lot of the classic attacks. So over time, the internet's become a more difficult structure to conduct some of these attacks on.
Great. Next, we got what storage backend are you using in Spark for storing the IPFIX data?
So
go ahead, Katherine.
I'll speak to this. Yeah,
please.
So for storage, we initially, for our prototype, were using HDFS. We added native support for S3, because the HDFS APIs are just really pretty slow in a lot of cases. In general, like Mothra is set up to use its own mechanisms to do partitioning and to do partition selection and access. So it's kind of a model of you throw a directory at it and you put any directory structure that'll work in HDFS modulo HDFS's capabilities with the Hadoop file system APIs, or local disk, or in S3 and S3 bucket, and possibly with a prefix within that. We'll let you work with it that way. So hope that helps answer your question.
It is also the case that one of the design goals for Mothra is to allow the using organization to have more flexibility in what storage structures they use. Silk, for example, classically made a lot of assumptions about its storage structure, and Mothra makes far less.
Yeah, Silk used a model of basically breaking things down by sensor and time, obviously, like by day. And then there is this idea of sensor and type, which would typically be sort of in, out, in web, out web. Mothra basically allows partitioning on arbitrary keys, although it does at the very base have that assumption that you're partitioning on time, because you pretty much always have to do that for data management purposes.
Shane, you started to say something?
Yeah, we're a little under 5 minutes, so we'll go with one more question. Last one in the queue for you both is what is the connection between application traffic and network threats?
Well, it's fairly simple. A lot of the times the network threat actors are there. They're not really targeting the technology, they're targeting the users. And the way to reach the users is through some application that the user wants to employ. So, for example, phishing email in terms of content or protocol level, it's just email. It only becomes significant as phishing email when you realize this is targeted to an individual who might release undesired information. A watering hole attack, which is where a website is corrupted that allows internal people to query local information, and the internal people inadvertently bring in malicious content with their local information. Well, in terms of things going on at the HTTP level or HTTPS level, it's just a normal web lookup. It only becomes significant as a watering hole attack when you realize one part of the web page is actually malicious. So that's application level that you need to be able to get into.
Great, thank you guys for that. Go ahead. I'm sorry, Katherine, go ahead.
Oh, it's okay. It also matters what you consider application level. Like in our stuff in this example, obviously DNS is being kind of interpreted at that level, and a lot of the layers of protocols and stuff, they're not as cut and dried as maybe once upon a time it seemed like they might be. DNS is so fundamental, but it's also kind of visible to everybody, and it's more detailed than some of the traditional things would track. Broadly, Tim mentioned SMTP, like subject lines and stuff like that, and issues around privacy with those. But those have been incredibly useful as indicators for, looking for certain patterns of subject lines will allow you to identify certain patterns of exploit behavior. Threat actors who are using an email campaign that uses always the same kind of shape of subject and the same kind of shape of attachment name, for example. So that's where getting into like the application layer can really be important for identifying what a threat is, despite the concerns about the privacy of users. And it's like everything in security, there's just a great deal of tension between how much security versus how much other desirable properties you have. It's a hard space.
Thanks for that addition, Katherine. Tim, we're a little bit under a minute. I wanted to give you just a quick chance to plug FlowCon, maybe where it's at this year. What's the status? Are you in the call for papers now, or a little bit about that?
I don't believe the call for papers for 2024 has yet been out. FlowCon is held every January. The location does vary. They haven't announced the next location yet. The previous one was in Santa Fe, New Mexico, a beautiful location. And it's an opportunity for people that are interested in this space to really network together. There's a variety of talks, usually around 30 of them, covering a lot of topics, and a very interactive and friendly crowd. So if you're interested in this space, attendance at FlowCon and even presentation at FlowCon is present. The archive of past presentations made across the 20 or so FlowCons that have previously occurred is online. You can go to www.flowcon.org, and that will actually bring you into some of the SEI's library of content, but specifically for FlowCon. And you can look at some of the past presentations that were made there. But it's a good group.
Great. Tim and Katherine, thank you for your discussion today. We appreciate you sharing your expertise. And we'd like to thank you all for attending today as well. Upon exiting, please hit the like button below and share the archive if you found value. Also, you can subscribe to the SEI's YouTube channel by clicking on the SEI seal in the lower right corner of the video window. Join us for our next webcast, which will be May 2nd. And the topic will be top 5 challenges to overcome your DevSecOps journeys with Hassan Yassar and Joe Yankel. Registration information is available on our website now and will be emailed out as well. Any questions from today's event, please send to info@sei.cmu.edu. Thanks, everyone. Have a great day.